Welcome to this second video on electric fields. In our previous video, we looked at the following items. First of all, we examined non-uniform fields, discussed their features and their production. We looked at the production of uniform electric fields. We examined the four rules for field lines. And we had a look at some equations and calculations that are relevant to non-uniform fields. In today's video, we'd like to have a look at the uniform fields between two charged plates and some of its applications. So first of all, we can see here we have in our diagram a DC power supply, which is able to generate a positively charged plate at the top here. It's hooked up to the positive terminal of the DC supply, and alternatively down the bottom we have the negatively charged plate as well, plate Y. So we've got a DC supply, positive plate on the top and negative plate on the bottom. Very similar, I suppose, to a capacitor in that sense. Between those two plates, we generate what we call a uniform electric field. Okay, you would recall that uniform means these field lines are parallel and equidistant with their spacing. These field lines on the very edge aren't typically uniform, and that's because they're running from the very, very edge of the plates. Okay, and these field lines, as you recall, travel perpendicular from the source to the destination. The spacing between the two plates can be measured in one of two ways. First of all, you can measure the potential difference, how many volts there are between the two top and bottom plates, the positive and the negative plates. Alternatively, we can look at the distance in meters, their physical separation. The electric field strength, which we give the value E, can be expressed in two ways when we're looking at uniform electric fields. The first is the traditional that we used in the non-uniform or point source electric field, whereby we consider a test charge and look at the force that's applied on that test charge. So the unit for that particular form of measurement of electric field is newtons per coulomb. The second alternative is to look at the potential difference that exists, the voltage from one plate to the other, from top to bottom, and then divide that by the distance of separation in meters. Another way to express an electric field between two plates is to describe it as the volts per meter. Okay, so there's our first two equations. If we were to place a positive test charge inside this electric field between the two plates, we find that there's a force pushing it towards the negative plate. Equation 1 can be rearranged. Instead of E equals F over Q, we can rearrange it and make F the subject. So we now have the force on the charged particle is the product of the electric field multiplied by the charge in coulombs. That gives me a resultant force in newtons. Work is also being done on the test charge by the electric field. So as it moves from the top to the bottom, there's work being done by this field, and it's expressed as W equals FD, the classic work equation. Before we go any further, some derivations. I must explain the following equations you can simply use off a formula sheet. However, if you'd like to see how they're derived, come with me for this journey. So we now want to substitute equation 3 into equation 4. Here we have equation 4, work equals force times distance. We're going to substitute in equation 3, where force is equal to the electric field times the charge. So where we have an F, I'm going to replace that with the EQ. We do so, we now have equation 5, which states work is equal to the electric field times the charge times the distance, the separation of the plates. Okay, there's our fifth equation. Now we're going to look at substituting equation 2 into equation 5 to derive one more equation. So equation 5, the one we just derived, work equals electric field strength times the charge times the separation distance. And equation 2 was the electric field strength equals the voltage divided by the distance. So where we have an E here in equation 5, I'm going to replace with the values V over D. You can see here that the divide by D and the multiply by D simply cancel out. And that leaves me with the new equation, equation 6, where work is equal to the voltage times the charge. Now work done by the electric field is equal to the gain in kinetic energy. The positive charge, as it moves from the top plate to the bottom plate, has work being done on it by the electric field, and it's gaining kinetic energy. It's moving. So it's gone from a rest to stationary position to having velocity or speed down the bottom. So it's gaining kinetic energy. So we can replace the delta EK with traditional kinetic energy equals half mv squared. So now we know the work being done by the field is equal to half mv squared. That's equation 7. If we now equate equation 6 and equation 7, here's equation 6 and equation 7. Both of them are equal to the work done in the electric field on the charge. The two left-hand sides are equal, which means the two right-hand sides are equal. So VQ equals a half mv squared is our final equation. And that's the end of our derivation. so we can look at our application of these various equations. In summary, these are the three main equations that you're asked to use to do calculations at VCE Physics. The first equation is E equals F over Q. The electric field strength is equal to the force divided by the charge. Second one, electric field strength is equal to the voltage divided by the separation distance in newtons per meter. And the third and final equation equates the work done or the energy of the charge as it moves from the top plate to the bottom plate. We can say that VQ is equal to half mv squared, where E is the electric field strength in newtons per coulomb or volts per meter. F is the force in newtons. Q is the charge in coulombs. V is the plate potential difference in voltage. D is the plate separation in meters. M is the mass of the charge in kilograms. And V is the speed of the charge in meters per second. One particular application we can look at with electric fields or uniform electric fields is that of a particle accelerator. I have here a basic schematic diagram of a simplified application of a simplified particle accelerator. This device fires electrons through a very strong electric field in which it is accelerated to extreme high speeds. Let's look at each step. First of all, the electron source. An electron gun uses either high current or light to release electrons from a metallic filament. So it injects the electrons. The electrons are accelerated between the large electric field or the large potential of the two plates to extremely high speeds. And finally, the electron emerges from the second plate and is now traveling extremely high speeds. If we put these three stages together, if you'd like to know more about particle accelerators, in particular the electron gun, please check out this following link. It's got some pretty impressive graphics and it goes into some detail explaining how an electron gun works. Just taking a quick look at this amazing little website, it demonstrates how an electron gun works, and it's the same concept of a heating element, a cathode, that emits electrons that are attracted to the anode, and we shoot them forward at a fraction of the speed of light. So let's have a look at how this works. We have a simulation. We can click on that. And we find that we run a current through our electrodes to heat them up. Electrons are being formed. We generate a potential difference between the two, and electrons will start shooting out with a beam. And this simulation tells us that the speed of these electrons is roughly 1 × 10⁷ meters per second. There's a lot more information here about the electron gun setup. We could certainly check that out as well. Here we have the basic components. We can look at the acceleration side of things. There we go, some theory as well. And we can also have a look at some exercises, some problem solving as well. So if people wanted to have a close look at the electron gun, try their skills, there's some definitions to fill in. There's some practice work as well, and more about the labeling of electron gun, and also there's some calculations that we can have a look at that show solutions as well. Let's look at some examples. Number one, a pair of oppositely charged electric plates are located in a vacuum and separated by a distance of 50 centimeters and a potential of 2000 volts. If a single electron is placed near the negative plate, calculate. So part A, the first part of this question, calculate the electron's kinetic energy when it reaches the positive plate. So here we have our two plates. An electron starts on the negative and travels across to the positive. Now note down the bottom, the mass of the electron, m(e), is 9.1 × 10⁻31 kilograms, and the charge of an electron, Q, is equal to 1.6 × 10⁻19 coulombs. So let's try this question. We've got a voltage of 2000 volts. We have a charge of 1.6 × 10⁻19 coulombs for an electron. The electron's kinetic energy is the question mark. Now the equation that relates these, before we're looking at the fact that the gain in kinetic energy is equal to the work done, which is equal to QV. So we can work out the kinetic energy of an electron as it's being accelerated between two plates of a potential difference by using the equation EK equals QV. I've color-coded these. EK is our question. Q, the charge, was 1.6 × 10⁻19 coulombs, and V, our voltage, was 2000 volts. If I multiply the two together, I end up with a kinetic energy of 3.2 × 10⁻16 joules. Part B of this question with the same setup, we want to calculate this time the electron's velocity when it reaches the positive plate. So we take the kinetic energy from our previous question in part A, 3.2 × 10⁻16 joules. We know the mass of the electron again is 9.1 × 10⁻31 kilograms. And we want to know its speed, its velocity when it reaches the second plate, when it's been accelerated between the large potential difference. So the equation that relates to these variables is the kinetic energy equation. EK equals a half mv squared. We can transpose to get v squared by itself, effectively multiplying both sides by 2 and then dividing by m. Finally, to get v by itself, we must take the square root of both sides. So v is equal to the square root of 2 times the kinetic energy divided by the mass. I simply sub in my values. Ek, the kinetic energy, was 3.2 by 10 to the negative 6 joules, and m, the mass, was 9.1 by 10 to the negative 31. I sub those values in and take the square root of my answer. I end up with a speed of 2.65 by 10 to the 7 meters per second. That's pretty quick. It's about 1/10 the speed of light. Part C. We want to calculate the electric field strength in volts per meter between the plates. So the potential difference was 2000 volts. The separation distance of the plates was 0.5 of a meter, or 50 centimeters. It must be in the right units. And we want to know the electric field strength in volts per meter. So the equation we use is electric field strength is equal to the potential difference divided by the separation distance. Ends up being 2000 divided by 0.5. Gives us an answer of 4000 volts per meter. Our second example. An electron gun is used to inject electrons into the linac of a synchrotron. The below figure shows a schematic diagram of the electron gun. The mass of an electron is 9.1 by 10 to the negative 31 kilograms, and the charge of an electron is 1.6 by 10 to the negative 19 coulombs. The electron gun is tested by first operating it at a low voltage. Using this voltage, the acceleration of the electron is 1.8 by 10 to the 15 meters per second squared. And our question is, what is the magnitude of the electric field acting on the electrons? So E, the electric field, is the question. We have the mass of an electron, 9.1 by 10 to the negative 31 kilograms. We have the charge of an electron, 1.6 by 10 to the negative 19. Now, electrons are negatively charged, but I'm looking for the magnitude, so I'm not worried about the negative sign for this equation. And the final bit of information we have is the acceleration of the electron is 1.8 by 10 to the 15 meters per second squared. Now, we haven't used acceleration before in this video. However, once I show you this equation, it should make sense. We know from our very first equation for electric field that we could derive the force of a charged particle in an electric field was equal to the electric field strength multiplied by the charge Q. We also know that force, Newton's second law, is equal to ma. Now these two forces on the left-hand side of both equations are equal, which means our two right-hand sides will be equal as well. So therefore we can say that E times Q equals M times A. And we want E the subject, so we divide both sides by Q, or effectively divide our Q across to the right-hand side. Now to work out the electric field from this point, we simply substitute in the values. So the mass was 9.1 by 10 to the negative 31 kilograms. The acceleration was a whopping 1.8 by 10 to the 15 meters per second, and the charge of the electron was 1.6 by 10 to the negative 19 coulombs. Put those values in, do the correct calculation, and we end up with an electric field strength of 1.02 by 10 to the 4 volts per meter. Finally, the accelerating voltage of the electron gun is now increased to its maximum value. The electrons now reach a speed of 4.6 by 10 to the 7 meters per second. We want to know what is the new voltage. V, large V for voltage is question mark. Mass of the electron. The charge of an electron is 1.6 by 10 to the negative 19 coulombs. And a little v, the speed, is 4.6 by 10 to the 7 meters per second. So we can use an energy approach. The work done by the electric field is V times Q, and it's equal to the gain in kinetic energy, half mv squared. We're after the big capital V. All we have to do is divide Q across. Easy way of representing that is we've already got 1 divided by 2. Let's divide this fraction by 1 over 2Q. That's the same as dividing Q across. Substitute our values in. So 1 over 2 lots of the charge of an electron, 1.6 by 10 to the negative 19. And we multiply that fraction by the mass of an electron, 9.1 by 10 to the negative 31. And we multiply it again by its speed, 4.6 by 10 to the 7, all squared. Important that we square. When we do that, we come up with a voltage of just over 6,000 volts. Thank you for watching this video. I hope you found this beneficial and clarified some understanding of uniform electric field theory. If you've enjoyed this, please like, share, comment, and subscribe. And as always, thanks for watching.